Hey, welcome back. Today we're going to be looking at, finally, how to apply our knitting patterns and woven curves and everything like that, and how to conform them to 3D surfaces. So you can see even with this one, we have nice kind of seams and stuff like that, just like you would construct a t-shirt or dress or some kind of garment or something like that. And we're still working with our initial building blocks, or these modules that we've kind of been setting up for this, just calling it like a modular approach. So in this case, this is the original basic knit, and we're just using the default Rubbertoy test geometry. And then we'll be applying the knitting from 2D using UV coordinates to the 3D surface of the geometry. And we'll be doing most of this through Vex. I go into this in more detail during the lesson. This is the fastest and most accurate and precise way I've found to really control where the cutting happens, where you have borders or seams, and then to be able to control the height that it's projected back out from the geometry, kind of like a texture, like a height map or something like that. So this is the most optimized and robust kind of controllable method that I've found to do this type of effect. So I'm excited to share it with you. So this is one of the examples. And then I also have here, this is kind of like a chainmail, like interlocking rings or circles or stuff like that. And that's just another kind of like bonus example, just again, using the same modular approach. We have the curves set out in 2D space and then just applying them to 3D space. And then over here, this is the basic standard knit, or I'm sorry, weave, just over, under. And here we're applying it to, again, to the same 3D surface. So even for like a carbon fiber type of texture or pattern or something like that, this would also be pretty useful. And lastly, this is kind of just like a crazy bonus example or something a little bit fun. And this one I was just setting up kind of a parameterized weave module. So basically we are going to create a bunch of patches or individual sections in this example of different kind of segments or different little unique portions of the cloth. And then that's going to be conformed again to the same 3D surface. So it should pop up just in a second here. This one's a pretty high res. It's kind of like a glitch style fabric or something like that. So we're able to, with each unique connected tile, to have different weave parameters for like the over under. So this is another interesting one to check out. So you can make a bunch of different randomizations, again, kind of like a glitch or just kind of like super technical type of fabric or something like that. Hopefully that's another interesting example for you to check out. Again, just using the same building blocks. So hopefully you have fun learning this Vex stuff. Hopefully it's not too technical. I tried to go through it really step by step, explaining pretty thoroughly what each function is doing and why it's needed. Feel free to let me know if you have any questions with the Vex code or anything like that in the comments, and I hope you enjoyed the lesson. All right, so we're gonna get started just with a fresh scene here. I'm gonna create a geometry node, just double click. So now we're at the geometry or the SOP context. And then I'm just gonna bring in some nodes. These should look pretty familiar to you if you watched any of the last 2 or 3 tutorials. I go through this pretty in depth. It's just our basic standard approach to creating a fabric or textile swatch or piece of fabric. So that we're going to continue on this kind of modular approach and build off of this. So you should be able to continue even substituting in any knit or crocheting or weaving or other patterns or stuff like that you've come up with. And we're going to basically look how we can apply this to a 3D surface this time. And I'm just going to start with a sphere. This is kind of the simplest 3D shape. So to start off with, it makes sense to just start with something pretty easy or basic. And the first thing I'm going to do is use the UV project node. And I'm going to switch this from orthographic projection. Orthographic is just like a single axis or a single plane. And we're going to do a polar projection, which is like a spherical projection. So this should better map to a sphere. And if you press the 5 key over the viewport, you can kind of see the unwrapping and how it looks. And then if you press the 1 key, you can get back into the 3D viewport. And this should be pretty good. You can also open up the attribute or the geometry spreadsheet. And by default, these appear on the vertices, which is usually the best place to start assigning your UVs. And one thing that I usually don't like or I want to get rid of is this third coordinate. So usually you have U and V coordinates. And if we go back here, this is like U and V. And then the other one, it doesn't make too much sense to keep. So I usually just use a UV transform. And I'm going to just get rid of that by scaling it to 0. So that's close enough. It's just like a super low number close enough to 0. Then we can do this vertex split. And what this does is I use this to promote the UV to a point attribute. But it does something kind of important. Instead of the attribute promote node, this will actually detach points that lie on the border. So if we look over here, when we did the UV mapping, this was where the seam was. Another thing you can do is if you do a group node like this, set it to edges here, and we do unshared edges. Once we move it down there, you can see these are all the borders of, if I press the 5 key again, the UV patch or the island. So the reason we want to detach these, or we want these to basically be made up of is unique points, is if we're going to swap between 3D and UV space. You can just do that by changing P and UV. We want those border points to be disconnected or non-continuous. And I'm just going to turn off the UV map visualization for this. So if we don't do this, and if we promote the geometry, we promote UV from vertex to point, you can see we have coincidental surfaces or overlapping surfaces, and that can cause a bunch of problems. So if we properly disconnect them, then you can see we have a much better representation of the flattened UV surface, like 2D geometry. So it's much like if you have a globe and you unwrap it, you want to have like a single surface and not like overlapping geometry that could cause problems. The last thing you might want to do is if you uncheck triangular poles, then you can see you have a nice square that perfectly fills this UV space. And let's just clean this up a little bit. The next thing I'm going to do is, once we have these like this, I can do a transform node over here. And what I want to do is move this geometry that we're usually working like this at the origin in a unit space on the XZ plane. And I want to rotate this 90 degrees. So now that we're kind of in the XY plane, and I also want to shift it 0.5 and 0.5 like that. And now we should be closer to something that I'm calling UV space. So you can see here that this is kind of overlapping or matching the basic position of this sphere once we've swapped it into UV space. So once we have this sphere separated out into both of these spaces, another thing you can use is the sequence blend node. And this is just kind of a visualization of what we're going to want to do. If we do this, you can blend between the two topologies like this. And you can see we're basically able to morph between the UV space and the 3D space pretty easily, or blend between them. One thing you can do that's very rudimentary is if you use the point deform, you can take this here as the mesh to deform, and you can take this UV patch, or the flattened geometry, and this would be the rest point lattice. And you can go here into the 3D point lattice, and this will give you like a basic deformation from the flattened to the 3D surface. But there's a lot of issues and small imperfections and stuff like that that you can get to. Just the way that this averages together samples and kind of blends and blurs things, it's never going to be that good of a result. And you usually don't have a ton of controls over how far you want the geometry to be lifted off the surface. And you can see that there's some pinching artifacts and stuff like that at the poles. And just delete that as well. So I usually like to use Vex for this type of thing. And this is a little bit advanced, but I'm going to try to walk through it slowly. So over here, this is basically the mesh in 3D space. And if I just hold Alt and drag and copy that, this is the mesh, but it's in UV space. And I'm just going to create one more thing. If we use a divide node and just turn off convex polygons, scroll all the way down and do remove shared edges. And then if you use the ends node, you can unroll the faces. You do unroll with shared points. I don't think it matters too much. And here we basically have the borders of the UV space, or the UV patch, or the UV island, however you want to call it. And I'm just going to connect these into the Wrangle in this order, like that, kind of clockwise. And what we're going to do is we're going to try to basically move this mesh into the 3D space and preserve as much information from this mesh as possible. And that's the reason I'm using Vex, basically, is to basically transfer over as much information and do this in the most precise way, while like preserving the structure and everything like that of the target geometry. And we're just doing this on a simple mesh, but this is really robust, and you can run it through really high point counts, and it can handle lots of geometry. Because it's Vex, it's multi-threaded and everything like that, so it runs pretty fast. And I'm going to start with just creating two variables here. One is going to be the prim num, and another one is going to be the prim UV. And you can put these next to each other like this. You're basically just declaring two variables that are undefined. And the reason I'm doing this is because I'm going to use this xyzdist function. And this basically assigns information or transfers information into these variables. So we leave them here uninitialized, or they don't basically have information, and then this function here will give them the information we want. And basically from the mesh that's in UV space, so that would be input number 2, we want to take the point position, the current point position of this 3D mesh, and then we can basically get the primitive number and primitive UV from the mesh that's in UV space. And right now, by default, it doesn't really do anything. But what we can do is we can read that information back in. If I get the primuv, this is basically how you can read any attribute. What we can do is something a little bit fancy here, and we can get, because this topology matches, we can get an attribute from the mesh that's in 3D space. So if we get a primuv, or basically attribute from this input number 1, which is going to be this input right here, we can get the P, or the position, point position, or surface position. And again, we can just use the primitive number and primitive UV from here. Like that. So now this basically gives us a really precise projection onto the surface in 3D space here. And we're not done yet. There's still some more stuff we can do, but this is the simplest way to basically use this function. So we're basically using the xyzdist to get this information from the geometry. And primitive number and primitive UV are special kind of primitive coordinates. It's different than the UV texture value or the UV attribute. Basically, each primitive number here has its own UV space, which is going to be 0 to 1 for each face or each primitive. So that's what this is doing. It's basically saying, tell me the closest primitive number. So that would be, again, this, once it's in 2D space like this, each point would find the nearest primitive number, and then it would find the nearest point on that primitive or on that face. And then we're saying, once we get that information, then find on 3D space the same primitive and the same coordinate on that primitive, and give me that surface value, and put that surface value onto the geometry, onto these input points. So that's this very basic way of doing this. This kind of a simple way of doing this things in the VEX code, but we're going to build off of this and make it a little bit more complex. But hopefully right now, this kind of makes sense to you. All right, so we're going to move forward a little bit. One thing I wanted to bring up quickly is just the technical name of these other UVs that I was talking about, the primuv. This is actually primitive parametric spaces, or something called implicit UVs. And you can find this link here. I'll put a link to it in the description. Basically, this is explaining it is that each triangle or each quad has implicit UVs, which are basically always there, or it's basically like just a property of the geometry itself. And by interpolating between the corners or moving between them by some amount, you get these kind of coordinate systems for a triangle or for a quad. And that's basically what we're taking advantage of here. You can read about this. This explains xyzdist and primuv and some other stuff like that in greater detail. But this is a super useful page of the Houdini documentation. Somewhat hard to find, somewhat hidden sometimes, but this describes a lot more of what I'm going through right now. So I'm just going to hold Alt and drag, and we can make another copy of this. And just again, always remember what inputs are going into what, and I'm just using these numbering systems or mechanisms to address the different wires or the different inputs here. So I'm just going to go ahead and add a little bit more into what we already typed out. One thing I want to do here with this input point position. So again, this is the flattened position here. I want to basically multiply the z value here by 0 to flatten it out. So let's just comment out this for a second. So we're not modifying p. And before we start anything, I can take p and I can multiply it and set it equal to, I'll make a vector here that's just 1, 1, 0. So I'm basically multiplying x by 1 or leaving it the same, multiplying y by 1 or leaving it the same, and I'm flattening or scaling z to 0. But instead of doing that to the point position here in 3D space or modifying the actual geometry, what I can do is just copy this, and if I multiply the p right here, when we use it with the function, this is going to just apply that math or look at the mesh here in UV space from the flattened 3D space. So it basically just ignores or discards the height information or the z value when we do that. And the reason I want to do that is if I just assign color to the output or the result of this function, you can see in most cases here, let's just go to the light background. In most cases here, this is a black or 0 value, and I don't know, maybe going to the gray would be a little bit better. I think all these are kind of hard to see. We could multiply it to make it bigger. But this is basically the distance that we are from this. So I want to basically ignore any height and look at the flattened curves when they're just in the two-dimensional space. And I want to know anything that's far away from these borders, because we can do some fancy things like that. If we want to cut them when they start to get too far away from the borders, we can do that. And that's something that's going to be really useful if you're even thinking about making fabrics or clothing or garments in 3D space. You would want to be able to cut along these borders or trim the fabric or stuff like that. So that's a pretty important technique that we want to be able to make sure that we can do here. So I'll just get rid of that. And I'm just going to name this here to a variable. And we could say that this is the distance to the surface, like that. So it's not changing the color anymore. It's just storing this internally into a variable for this Wrangle code. And we could comment that out and go back to 3D space like this. Another thing we want to do is maybe get this distance here to the borders. And that's going to be a little bit different. Basically, if we get distance to here, any value inside of this grid is going to be 0 or close to it. But here, any value here is going to go back up and increase. So it will increase in both directions. But we can use this surface as well and find things that are inside of it to negate, or to basically set this here as like a negative value and this here as a positive value. And that will help us know even better where to cut. So let's make another variable, and we'll call this distance to border. And this time I'm just going to use the distance function. We can use minpose, and we can use this input number 3, and we can set this to the same p multiplied by 110 to get the same like 2D projection. And we want to find the distance. This is basically going to return the nearest point on the border here, from here to here. And I can reuse the p times 110. And we should be good like that. And then if we want to compute the final distance, we'll just call this dist here. We can have distance to border, and we can multiply that by the sign, basically seeing if this is negative or positive, and we're going to do the distance to surface, and I'm just going to subtract like a really small threshold from that. So this is going to give us negative numbers for anything that's inside of the surface or overlapping the surface, and then it's going to give us a positive number for anything that's outside or not overlapping with the surface. So if I assign color now to distance, we should see something a little bit different. We see we have kind of have negative and positive numbers here. And let's not move the position yet. Let's leave it right there. And this attribute adjust color, this is something that's pretty useful to like remap or visualize color if you just have a value assigned to it. Let's take the remap. We can take our source attribute here as CD, and you can see here we're going closer to red now. Let's go negative 0.25.5. And you can kind of see we're able to more precisely work with this information. So if we even wanted to cut inwards from the seams, we could do something like that. So all this stuff is a little bit more important to keep track of, or it just lets you have more flexibility with this kind of stuff. So that dist value is pretty important, and I think we should be okay to keep going with this for right now. The next thing I'm going to do is let's just assign the P value to dist. So that's going to put, basically the points are going to represent that distance now. So each axis or each value, x, y, z, is going to be the same number. So we just get this line, but that's okay. And then here, instead of assigning P to the final surface position, we could put this maybe as rest. So we have this temporary number. And then I'm just going to use the clip node, and this will let us cut very cleanly above or below this clipping plane. Right now I'm just going to set it to keep any primitives that are below the plane. This is basically negative numbers. So when we did this sign, this is areas that are inside of this two-dimensional mesh. So anything inside of this, it will keep. And then we can use the attribute swap, and we can use this to move the rest information into the P attribute, like that. So that's pretty handy. And if we want to look at this distance here, now you can see we're able to very cleanly cut on a straight line inward from those seam or border areas if we want, or if we go into the positive, we would have basically a little bit of an overlap. So I should be able to turn on the point numbers. Let's just take a look here where it's changing. And if you want them overlapping or a little bit extra, we should be able to do that. So you could have some extra information if you wanted to. Usually I like to keep a little bit of a gap, and then I can snap or join those points together using the polypath node. And this usually lets you get a more like continuous or rounded bit of information there. So you just have to increase the threshold a little bit. And then once you start to subdivide everything, let's just do a sweep. Then you get nice continuous curves. So you can see we're still having overlapping issues, or we're still like kind of flattened to the geometry, and that's the last thing we're gonna want to fix. All right, so lastly, what we do here when we take the rest position and when we fill it with the mesh that's in 3D space like this, we can basically get the surface normal, or the primitive normal. That's basically the distance or the direction that the faces are pointing. And before, when we were basically telling it to ignore the Z position or the Z information, we can kind of do the opposite of that. And we're basically going to only keep or only get the Z information. So the way we're going to do that is basically using this prim normal function. And this is another special function, kind of like primuv, but it only gets the interpolated or like the smoothed direction that the surface is pointing. So again, we want this to be the mesh that's in 3D space, this first input here. And we can again just use prim num and primuv. It's the same information there. And right now this is just the normal vector or the direction that the surface is pointing. But if we scale it by p dot z, then we'll have a little bit more usefulness from this. And we want to do this before we basically adjust p at all. So I'm going to actually put that back, and I'm going to just Control X to cut that, and I'm just going to do this. This is going to be the very last thing we're going to do, is change this input point position. And right here, we can take this again and just add to it. We're going to add to it in the normal direction by some amount in Z that's like scaled by this input distance here. So basically, if we were to take this, we have to do it from Y here, because this is like applying scale before we rotate or translate. You can see that this is all being preserved. So if we scale here, we're doing the same adjustment. So now we basically have much cleaner, controllable, and more precise way to transfer or transport this from 2D space to the 3D surface position. And this is kind of a similar technique of applying like a height map or a normal map, but we're actually doing it with geometry. And this is a super effective technique. Even if you're not doing it with knitting or weaving, you can even do it just with like individual surfaces, and the same concepts and stuff like that will carry over. So just as a quick example, if you do another grid, we'll just put this quickly into UV space like that. Just offset it. So it's from 0 to 1. And we can do the labs lot subdivision. And we can reduce the threshold here, like that. And let's do just a quick attribute randomize. we can do this per primitive, and we want this to be a single dimension, and I'm just going to set this to Z scale. So this will work with the poly extrude, and if we just set this distance to 1 for local control, we can use that Z scale. So we basically have these faces getting multiplied or influenced by that randomized attribute that's randomized per face. I think if we do individual elements, that will even keep like these connected ones. And maybe the inset, we could add a little bit of that. Or sometimes if it doesn't let you do it too much, you can just do this transform extruded front and maybe reduce it that way. So we have some kind of crazy weird surface like this, and instead of working with the knitted curves like this, we can just plug that into here. And I think my distance here is just going the wrong way. Might actually be better just to kind of flip this around. So here we can just set this to like -1 like that. And let's just reverse the faces like that. And this is just an example. It's nothing special, but this is just showing you basically any flattened like surface that you're modeling like that, even height fields or anything, you can kind of quickly transfer this onto 3D geometry very quickly. So let's just go back to the knitting. I'm just going to move this over here. And the last thing I'm going to do is just show you how you can make this braiding work even better. So let's reduce this a little bit more. This is basically still using the p-scale attribute that we're setting from all the way up here. So that's pretty nice that it will automatically scale or adapt no matter how dense or sparse your knitting pattern is. But I'm going to make this really thin at first, so we basically don't have any intersections or overlaps. And this is going to be the rest position. So I'll plug it into the other input here. And I'm just going to make another copy of this. And this time we could set this to like 0.25 or something like that. So this is getting as the rest position, the smaller ones. And then this is the current or like kind of target position. And if we want to adjust the thickness or the kind of like extrusion amount, we can do that as well. And then I'm just going to use the Detangle node. So if you set the previous position here to rest, and we can reduce the thickness, pretty small, this should resolve any of these like penetrations or areas that it was going to overlap. So it's kind of like a hack that's, I think the cloth solver or Vellum uses it, but you can use it just to find like a single step penetration like this. It's pretty useful. You could subdivide it either before or after the detangling is done to add even more like resolution to the collisions or the penetration kind of resolution. You might even want to add more thickness, like a really thick knit or thick blanket or something like that. And you can keep playing with subdivide and stuff like that and get some interesting results. So the really useful thing about this is that not even just with a sphere or basic shapes, but we can even take the test geometry of this Rubbertoy. And this comes with UV attributes. You can see this has many different islands or many different patches. So we should be able to do the same thing with this. I'm just going to copy everything over. We should be okay with those. Let's just put that there. And let's do this. So you can see we do have some issues here where it's basically having trouble finding from one patch or one area to another. And the quickest or like kind of laziest or easiest way to fix this is if you just use the for each connected piece method. So this gives you some nodes to work with, and basically the connectivity is assigning a class attribute per 3D connected in patch or geometry. But if you say use UV connectivity, then it's basically looking at UV space, and each of these patches here will get a unique class number assigned to them. So you can just put these for eaches around here like that. And now you shouldn't have those issues with finding the wrong patch or the wrong surface. And we should be able to keep these other ones. I'm going to do the polypath inside of the loop, so we make sure that this is just connecting information. We could maybe even try it outside. Sometimes it gets a little bit crazy, but it might be okay. So you can see maybe some aren't finding neighbor points to connect with, but with complex 3D surfaces, that's sometimes an issue you can never really resolve. Basically, if you imagine clothing or t-shirts or things like that, you generally need to have seams or cuts in some places. There's never really a way to perfectly connect or thread every single knit or piece together. One thing you can do if you want on the sweep nodes, if you set end cap type to grid, you can get some rounded capped tubes, and that can make things look a little bit more clean. It kind of hides the insides or stuff like that. And again, all this stuff is super modular or flexible. The weaving patterns or things like that, you should be able to pump those in pretty easily. I'm just going to work with a little bit higher resolution or a denser knit for right now. And let's go back. Maybe we don't want as many subdivisions. Just make sure we're not making too much geometry. Let's turn off this one. So I'm setting this here to be 0.85, so it should try to make it a little bit thicker. You can, let's just go all the way up to 1. So you can see now, once you have a little bit denser, it looks like a more traditional kind of machined textile or fabric. You can see the seams here, they still look a little bit weird, but once you start to add in more threads and stuff like that, it will look a little bit more realistic or more like an actual kind of like fabricated or real piece of woven material. And again, if you want to keep playing with some of these parameters here, you can adjust like the thickness, how much the stuff is going to stick out. You can even go negative if you want to flip these things around so that the other side is going to be poking out or sticking out. And again, you could switch over to weaving or any other knit patterns or stuff like that. I was going with earlier, or you might have come up with your own, you could try those as well. So hopefully this gets you through some of the more technical stuff. I promise you this is the most technical this stuff is going to get for the knitting or weaving, but basically to apply all this stuff to a 3D surface, and if you want to be able to control as much as possible, like work with these seams, maybe you want to put in your own kind of filler fabric here, or your own filler curves or geometry, you can do that. And again, being able to scale the distance that it's, again, putting back out from the geometry. This, to me, is the most robust and kind of quickest and most optimized method to do it. It is a bit technical, but hopefully it wasn't too dry. Hopefully it didn't put you to sleep walking through this math, and hopefully I kind of broke it down into more manageable steps and it wasn't too overwhelming.